And this talk is by Giuseppina Fabbiano. So maybe you could make your screen, you could share your screen already. Yes, okay, there we are. And Giuseppina will be talking about the Virtual Observatory. Please go ahead. We cannot hear you. Maybe you have your, maybe you're still muted.
Yes, okay.
Yes, it's fine now. Yes, please go ahead.
Good. So I will say just good morning or good afternoon. I should probably introduce myself a bit because I'm not part of your ESO community. I'm an X-ray astronomer, but I also do multi-wavelength research on galaxy evolution, and galaxy X-ray sources. And I mostly work with Chandra data. It's the Great Observatory of NASA, and I am the head of the Chandra Data Systems Division. I've also been involved with the IVOA beginning, and I'm currently a member of the exec. I've been chair of the exec in the past. I also like to introduce Janet, who has contributed to this presentation. Janet Evans is the present chair of the IVOA Technical Coordination Group, and she's here and she's be available to give her wisdom on technical questions. Okay. Oh, this thing doesn't move. Let's try this. Okay. So the IVOA, International Virtual Observatory Alliance, is 20 years old and started really here at ESO, and that's a picture from then. And it's the worldwide collaboration for interoperability and data standards in astronomy. The oh dear, this thing really, okay. Okay, I'm giving here a timeline of data access and interoperability going now to open science. Well, basically we started on in the 60s with the beginning of computer connectivity, ARPANET, internet. And then in the 70s, we have email and standards for encoding messages, which allow email. In the 80s, World Wide Web started as CERN, so Global Hyperlinked Information Systems. In the 90s, web browsers started again as CERN and Slack, but then became common use. In the decade of the year 2000, the concept of data access and interoperability take place, and therefore the Virtual Observatory. The next decade sees the growth in societal data interoperability projects, both in Europe, in the US, basically worldwide. And in particular, the definition of the FAIR principle for data. So the data ought to be findable, accessible, interoperable, and reusable. And now, new challenge, reproducibility and open science. So we as a community have been early adopters of all these developments. In particular, we start with email, of course, with the distributed worldwide. Email is a very good way of communicating. Follow that with the data services. For example, NED and SIMBAD, the introduction of FITS, and also in the US, the NASA data infrastructure, which still functions with the archive and mission centers. ADS was started in my institution, actually, at SAO, the Center for Astrophysics, which gives access to the literature and provides data literature links. I'm sure you all use that. And then the Virtual Observatory, where the idea is to have easy access to data, reuse, and the interoperability. So some of the concepts we're also talking about today. Followed by European VO initiatives and the use of Virtual Observatory IVOA standards as part of the infrastructure, the data infrastructure in major data centers worldwide, mostly in the US and in Europe, but also probably in other places. And so now this is an open box, see what we can put in there. So what is the Virtual Observatory? From the astronomer point of view, it's a multi-wavelength, multi-messenger digital sky that can be searched, visualized, and analyzed in a new and innovative way. From the point of view of the data provider, is the latest stage of good data practices in astronomy. So, well, basically we started that each data center or archive had a different file structure, metadata, table organization. So the data is there, but it takes work to access it, especially if you want to do multi-wavelength analysis and use several data sets together. FITS provided a first standardization and was adopted by the community. And then the Virtual Observatory is kind of the natural progression towards interoperability of data, but also services and tools. So the Virtual Observatory, I see that as basically as a three-pronged initiative that produces new science. So we start on the top with data management and access. So one thing which has been proven by experience is that if we have easy data access in well-managed archives, we have data reuse, we have new science, and increase of public awareness on the data. And I'm giving an example that's close to my heart because it comes from the Chandra Observatory, but the Space Telescope Baltimore has similar results. So this is a plot of the percentage of Chandra exposure time published versus years of in the archive. So the mission has been there for 20 years. And as you can see here, that now, after 19, 20 years, 70% of the Chandra data is being published more than 4 times. And that's not publications from the original team. This is use of archival data, so it's new science. Okay. Next thing, interoperability. So the idea is to have an environment for the astronomer where you can access your data, you can access your tools, you can access the literature, and you can do this in a fairly easy, seamless, flowing way. So, and this is something that the Virtual Observatory and the use of Virtual Observatory protocols allows. And finally, so far I wanted to give an example of this is a thread that's based on the Chandra source catalog. And if, for example, we start here, so a user will use the Chandra data and we have interfaces where you can do that. Our catalog is a bit special as a catalog because it has tables of data of source properties, but it also gives data products. So per the field of observation coadded together and also per sources, you have a mini data cube and you can have our 4-dimensional data, you can have a spectrum, a light curve, etc. So a user can derive, choose the data from the observatory. They can pipe seamlessly this information to TopCat. TopCat can access the VO and maybe download other properties for these sources, plot one against the other. We all do all this all the time. You want to select some sources that have a particular different, say, spectrum, and you want to see which of those is in an image. So you can just pipe that by using VO protocols, in particular SAMP, to an image and so forth, and continue your analysis. You can take a spectrum from a source, you can do more detailed model fitting, for example, and now you can do all of that and record it in a Jupyter notebooks. All of this is done by using IVOA standards. Here is the list. And there are more newer standards, including adding DOIs to data products, data identifiers that will be available with the upcoming version CSC 2.1 of our catalog. And the final prong is the big data. It's a big concern. It's an exciting concern that we all have now. And so it's work on workspaces, collaboration tools, data mining tools, and services, and some of the stuff we're discussing here today. So the Virtual Observatory, I said it, and I'm repeating, it's definitely fair. Just to show you that we are a real organization, although it's kind of a virtual organization. We have a structure, and with an exec that coordinates various activities, and there are meetings twice a year. Everybody's free to participate. Please come and join one of our working of interest group and contribute to the process. What do? We create standards, and there are standards for data access and analysis. And here is a list of topics for which we do have standards. I'm not going to go through them in detail. We also have standards, so the people at data centers can create data products that are compatible with the Virtual Observatory. For example, definition of metadata, VO access services, and how to register your services in the IVOA registry. And finally, one thing that the IVOA produces are also data models. And a data model organizes elements of data and standardizes how they relate to one another and to the properties of real-world entities. I'm going to give an example. There's also Virtual Observatory data model language that enables the development of data models with standardized tags that identify each element of the model. And finally, an annotation syntax that allows data providers to match their data and their data structure and the data product metadata to the models. And software tools then can use the data models and annotation syntax to interpret the data and implement scientific algorithms to perform functions without knowing the innards of each data archive. Here is the example I wanted to show. So say we have a data modeler, a data provider, and a scientist. So the data modeler will design, for example, the source data model. So the source has some properties like position, time, flux, etc. And the data provider will map their source catalogs, and these are different data providers, to the source model. And they know what their metadata means and what their column means, and so they can tag them. So if a scientist then makes a model-based query to the various catalog, for example, we'll say, get the source which measure at this time and this position. The fact that all this infrastructure is being tagged together according to a model will result in the scientists being able to download what they need for their research quite easily without knowing the details. So if you want to find out about more about the IVOA standards, and we have a new IVOA architecture document that Janet and other collaborators have put together, and you can find that on the web. Please give it a look. And there also there you find all the data models in their nitty-gritty details and standards. So let's go to what we're supposed to talk about today, reproducibility and open science. What is the motivation? Well, I think the motivation really starts with some dodgy results in publications, mostly in medical and biological sciences. Nature, for example, was quite vocal on this, stuff that couldn't be reproduced. But now it's being requested by journals and funding agencies. And so the idea, as we've been discussing in this meeting, is the data behind the published picture, a plot, should be made available, and the results should be reproducible. This is the page from NASA, Open Science Initiative, which is something that started fairly recently. Basically, it's got 4 prongs, and some of this has been discussed here. So the fact that the science should be accessible, so data, tools, and software, documentation, this is the FAIR principle. They should be reproducible, that's what we're discussing today. But also there is attention to the societal importance of data and science kind of opening to diverse people in the organization. And there was some of it discussed also yesterday. And the fact that the scientific process and results should be understandable by the public, which, I mean, at the end, they pay for it. This is another web page from NASA advertising an initiative that I think they're going to start pretty soon, how to really move to this new paradigm. So, but how do you do it? There are some issues, and some of this was discussed here. For example, you want to have access, you should have access to the original archival data, but sometimes there are different versions of data in the archive. Maybe the original version, the one that you use in the paper you want to reproduce, is not easily available. You want to have access to the original calibration. But again, original calibration might have been replaced by more recent, better products. So access to the original reduction software or pipeline, and software evolves, we all know that. And the original version may not be easily available. And even if it's available, it might not be able to run on your computer nowadays. You want to have access to the published digital data product for comparison and further analysis. And especially if we look backward, this comparison will not be identical because of these issues that I have mentioned, but should be acceptable within statistical and systematic uncertainties. For the future, maybe we can do better. So in a plot, what we have various archives, we have analysis software, we get the data from the archives, we analyze it. Here we have the results. And the results, we want these results basically to be self-documenting. So the results should tell us which type of data was used, the calibration history, the analysis tool version, and all that. So what are the ways forward? Some ideas how we could achieve reproducibility. Well, one way, of course, which we're familiar with, is self-documenting result. And so we should preserve all the history in the metadata, and that includes provenance, so instrument, archive, standard reduction, and also user analysis, which software and workflows were used. This works in the FIT paradigm. We do some of that already. What about new formats? And this is a job for the DOA. Some of the standards, maybe they need to be looked at and extended for the future. Identifiers. DOIs are becoming common, and we use them already for publications, but they should be used, and they are starting to be used to label data. For example, MAST does that, and the Chandra Archive is starting to do it. And in principle, they could be used to label, and probably in some cases it already happened with Zenodo, to use users' data and the software that was used for the publication. We need to link all this information. So this is a job for probably an extension of ADS. Already ADS can link data to publications. A new thing would be to probably link the data to the final, by data I mean the archival data, to the final data products, the result data, and the software used to produce it. But this result and software repositories need to be established and need to be curated. Where do they go? Archives, maybe. Journals, maybe in some cases. The funding agencies, for example, NASA is thinking to do a central repository for this stuff. Does it make sense? Okay, another way forward is science platforms. They're becoming pretty much what we do. So the idea is to make data and tools available in one environment. Bring or save your own tools, and Docker containers have been mentioned. That could be a good mechanism. You can work with data from accessible archives, collaborate with colleagues in data analysis and results, build Jupyter notebooks, for example, to preserve analysis step and reproducibility. Then you tag everything with UIs and publish and save it all. So that's the future. How can we help in the AVOA? So I just put here to remind us that there is a new bubble, reproducibility and open science, which is kind of already there in the three old bubbles of the AVOA in my sketch here. So one thing that we should do is to look at the standards and see if the reproducibility is covered and what extensions are needed, similarly for the data models. But there's also a place for data centers and archives. I think they can help because they preserve a hierarchy of data products, starting from telescope data, raw data, calibration and calibrated data products at various levels. They curate data that utilize the IVOA standard and registers the services, produce high-level data products, for example, co-added data in the Chandra archive. They produce catalogs in some cases, and the catalogs could be tabular, but could be associated with data products, as we have done with Chandra. So by using IVOA standards and documenting data and software, archive can produce and do produce open science ready data. I think that's an important thing to keep in mind. And also by providing user workflow capability with documented software, which is a function that some data centers do, the final results of the user will be more open science ready. And a way of doing that is to instantiate some of these in Python workflows and Jupyter notebooks that people use. So in conclusion, how can we achieve reproducibility and open science? Well, three possibilities that's for discussion are self-documenting results. There is a tradition that we have in astronomy for that. Use of identifiers, DOE, for data, publication, user data, and software to link it all together. And then use of science platform, so to make data and tools available in one environment and uptake of perhaps of Docker's containers. And the IVOA, I think, is well poised to meet the challenges with the completion, extension, or new virtual observatory standards, particularly provenance, DOI, science platform workflows, and data models, and maybe other areas. And thank you.
Thank you for this very nice talk. We have a number of questions. I will just read them out. So first of all, Sundar Srinivasan asks whether you can tell us about the VOSI table format that was mentioned yesterday by Stephen Quinn.
Let me stop sharing this so we can see each other. Okay, VO table format. Well, it's one of the formats that it's a standard of the VO. If you go to the web page, you find some details.
I think Sundar was referring to the VOSI table, so a new form of the VO table, as we understood yesterday.
Oh, okay.
Is that right?
All right. So this is, I think it's a question for Janet, who's the total expert in this stuff.
I mean, I can't talk about it just off the top of my head because I'm not dealing with them at that level, but the documentation, I can try and find it and I'll put it up on the Slack channel so that folks have a pointer to it.
Okay, I think that would be very helpful. Yes, and that's what Sundar says as well. Okay, thank you. Then we have a question from Ushin Greener. And he's asking, in terms of reproducibility of data products in an evolving software environment, what steps do you recommend for locking in versions such as libraries, code, calibrations, etc.? Would you favor something like a Git commit, hash, a Docker container, notebooks, written documentation with a list of requirements? And then he says some of this is answered already. But yeah.
Well, I mean, I think some of this we discussed, and then I think it's an evolving discussion. I would say all of the above and see what we can do better. We haven't had much experience with Docker container. That sounds very promising as a way to do, maybe a bit work intensive for the user, but I don't know. People use notebooks, and that's definitely a good practice.
Yeah, it's a complicated problem, isn't it?
It's a complicated problem, and I think it's an open discussion that we'll have to try and see what comes out of it, as these things.
And then just to add, Peppy, it might be a mixed bag. It depends on how big your project is, how small your project is. You know, I think it might be all of the above for a very long time.
Yeah.
Right.
Okay, good. Thank you. Are there any further questions? I don't see anything in the Slack, and the chat window is also empty. So if not, thank you again, Giuseppina. That was a very nice, informative